Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at an introduction to optimum filtering. There's a whole class of things known as optimum filters, and the general nature of those filters depends upon what it is you're trying to optimize. We're going to look at one type of optimum filter. We're going to look at filters that will allow us to maximize signal-to-noise ratios for low-pass message signals that are corrupted by broadband white noise processes. That's all we're going to do. So, let's jump right in. Optimum filtering. Previously, I mentioned in a previous video that it's impossible to improve signal-to-noise ratio or clarity simply by using a broadband amplifier. So we cannot improve signal-to-noise ratio or clarity simply through amplification. Oops. My eraser got out of the way. Cannot improve signal-to-noise ratio simply through amplification. Right. We cannot improve signal-to-noise ratio or clarity simply through amplification. So this is the situation that we're kind of going to be looking at today. I'm going to have, say, a low-pass type message. We'll call this the message power spectral density, S sub m. And there will be a noise power spectral density. We'll call that S sub n. And it's white. It extends to plus and minus infinity. And there is zero frequency. And we're going to be, say, investigating my message and noise combination over some spectral width B. So B is my interesting spectral width. Okay? Now, it's possible, if we're clever about it, it's possible to increase signal-to-noise ratio or clarity by attenuating frequencies where the noise is strong but the message is weak. Okay? It's possible to increase the signal-to-noise ratio by designing a filter that will attenuate frequency content where the noise power spectral density is large compared to the power spectral density of my message. However, such a filter might reduce the fidelity a filter that improves clarity might distort the message by attenuating some of the higher frequency content. When we distort the message, we reduce fidelity. Alright? If we distort a message, we reduce its fidelity. Okay? So the question for us is, can we design, with knowledge of the power spectral density of my message and the power spectral density of my noise, can I design a filter in some optimum way so as to maximize clarity while minimizing loss of fidelity? So our goal, design a filter H optimum that maximizes signal to noise ratio or clarity while minimizing distortion or loss of fidelity. Okay, that's what we want to do. Our goal is to design a filter, H optimum, that maximizes signal to noise ratio while also minimizing distortion or loss of fidelity. All right. Let's do it this way. This will be my optimum filter, to be determined. To be determined. And at the input, I'm going to have a message and noise. So, all right, this is incoming noise. Alright, and this is my message. Alright, and what I'm going to do is I'm going to assume that at the output I have my message plus an M sub epsilon distortion term plus a filtered noise term. Let me write down what all these things are. So my message plus a distortion term is going to be my distorted message. This is my original message. This is an additive distortion term. And we'll pretend that it's a noise term since it's something I don't desire. So it's going to be a distortion noise term. And this is going to be my filtered noise, also known as channel noise. Filtered noise is sometimes referred to as channel noise, thus the N sub C. Okay? So, we're assuming that my distortion noise term adds to my filtered or channel noise term. So what I'm going to do is I'm going to look at each of those noise terms individually, look at their noise powers, and then add them up. Let's begin by looking at the distortion noise. All right. If I do this, if I let my message be applied to the input of my optimum filter, the output is the message plus the distortion And if I also subtract the original message from the message plus distortion, I get the distortion term in isolation. So all of this can be written as H optimum minus 1, some filter, H optimum minus 1. If I apply my message signal to H optimum minus 1, I get out the distortion noise term. All right? Let's go to the next page. I'm interested in the distortion noise power. My distortion noise power equals let me write it down, then I'll remind you of something. Integral from minus infinity to plus infinity okay. Recall that the output power, the power at the output of any linear system when a random process is applied is this. The output power is integral from minus infinity to plus infinity of the input power spectral density times, well, not necessarily talking in a general sense about an optimum filter. Okay, so if I have a linear system and I apply at the input a signal with power spectral density capital S sub x, and the linear system has transfer function h of f, then the power at the output can be found through this integral, and that's the integral that I've applied over here to find the distortion noise power. All right? All right. So that's as far as we can actually take that. The second thing I'm interested in is channel noise. Channel noise. The channel noise power is simply this. P sub c equals the integral from minus infinity to plus infinity okay? And this is the power spectral density that's power spectral density of the incoming noise. Once again, I've applied this relationship. Okay? All right, so the total noise is the distortion noise power plus the channel noise power. So the total noise power total noise power at the output of my linear system is going to be the distortion noise power plus the channel noise power. All right, let's go to the next page and expand that out. Adding the channel and distortion noise powers gives me the following. Okay? Adding the distortion noise and channel noise powers gets me that far. All right, then we've got to simplify that. As they say, the steps are straightforward but tedious. To simplify this particular integral, I'm going to provide all of the steps to you in a handout, which you should consider mandatory reading. But after several steps, I get the following. Hang on, I'll tell you what SR is in just a second. All right. In this relationship, SR of F is the message power spectral density added to the noise power spectral density. Okay? All right, let's look at this integral result in the middle of the page and recall some things. First of all, power spectral density is always real and positive. Okay? It's always real, it's always positive. If I take the absolute value squared of any complex number, I get something that is also real and positive. You'll also notice this plus sign right there. So my integrand in the integral in the middle of the page here involves two terms, both of which are real and positive and added together. The integrand of the integral here in the middle of the page is real and positive. For that reason, it is impossible to reduce the output noise power to 0. All right, that even what that's saying is even through the process of optimum filtering, excuse me, I cannot eliminate noise. I just can't do that. What I can do is minimize noise. We're going to minimize the noise. So how do we do that? Well, notice that the first part of my integrand is the only one that depends on my optimum filter characteristic. The second part of my integrand is this piece. The second part of my integrand is independent of my optimum filter. So that term has got to remain. The second part, the part of my integrand that I've underlined in green, will always remain no matter what I choose as my optimum filter. But due to this minus sign, it is possible for me to choose an optimum filter in such a way as that first term completely cancels out, thereby minimizing my output noise power. Okay? So let's write down the result. So we can minimize output noise power by choosing H optimum to eliminate first term in the integral on the last page. Okay? And in fact, it looks like this. H optimum equals the message power spectral density divided by the sum of the message power spectral density and the noise power spectral density. That's it. All right. Of course, now the trick is to design that filter using circuit elements and chips and stuff like that. So this is the form of the optimum filter, given that you know what the message power spectral density and noise power spectral densities are. Designing it in practice, that can be a little more challenging. Okay? The optimum filter for this purpose, the purpose of maximizing signal-to-noise ratio while minimizing loss of fidelity in the presence of broadband white noise, this type of optimum filter is known as a Wiener-Hop filter. HOPF. Named after a couple of German engineers who investigated this type of optimum filtering way back in the 30s and 40s. It's also commonly just referred to as a Wiener filter. Okay? All right, so assuming that we eliminate the first term in the integral on the middle of the page, in the middle of the last page, my minimum output noise power is And interestingly enough, if you carefully take a look at this, you'll notice that this is integral from minus infinity to plus infinity of my noise power spectral density times my optimum filter. And of course the units are watts. So this is the minimum output noise power after optimum filtering. Okay? All right, so let's do an example and take a look at how this might look. Let's assume that I have a message power spectral density Let's assume I have a message power spectral density that looks something like that. That's a low pass signal. All right, and we'll assume that my message or my noise power spectral density is N0/2. All right, and once again, this is kind of what I'm looking at. I've got a low pass type of message, and I've got broadband white noise with a constant power spectral density, and I am interrogating this noise and message combination over some bandwidth B. All right, B is not necessarily the bandwidth of my message. It's the bandwidth over which I'm interested in investigating the combination of message and noise. Okay, B is not the bandwidth of my message. And oh, by the way, I noticed as I'm looking ahead into my notes on the next couple of pages that I solved this example in radian frequencies. I apologize for switching, but I'm going to go ahead and proceed using radian frequencies. My noise power, calculating this from a radian frequency perspective, is 1 over 2 pi, integral from minus infinity to plus infinity, of my noise power spectral density, n naught over 2 d omega, and that is just n naught b over 2 pi. Earlier when I calculated the noise power, I apologize, that should not be from minus infinity to plus infinity, that should be from minus b to b. There. The noise. This is P sub n is the noise power in a bandwidth B centered at the origin. Earlier in the previous video on white noise, we did not have the 2 pi in the denominator because I was solving everything in non-radian frequencies. Okay, so this is the noise power in a bandwidth B in radian frequency. All right, so let's take a look at the input signal to noise ratio, or the prior to filtering. So I'm going to have, this is my optimum filter, and this will be the input side. This will have an input signal to noise ratio at the input, and we'll have a signal to noise ratio at the output. All right, let's look at the input signal to noise ratio. So the signal to noise ratio at the input is the message power divided by the noise power. 1 over the noise power is just 2 pi over n naught b. That is 1 over the noise power. And then I'm going to multiply this times 2 times 1 over 2 pi times the integral from 0 to b of my message power spectral density, which is 2 alpha over alpha squared plus omega squared d omega. Okay? All right. Simplifying this just a little bit, we get 2 over n naught b, integral from 0 to b, 2 alpha over alpha squared plus omega squared d omega. And now I'm going to apply an integral table result that I found. Says the integral of 1 over c squared plus x squared dx equals the arctangent, or 1 over c times the arctangent of x over c. Okay, I'm going to apply that integral relationship that I found in a back of a calculus book or something somewhere. So applying this, I get 4 alpha over n naught b times 1 over alpha arctangent of omega over alpha evaluated from 0 to my bandwidth B. And this is 4 over N naught B times arctangent of B over alpha. Okay? Now, that particular result is, it is what it is. It's not particularly interesting in and of itself. But let's look what happens. As sort of look over here as an aside, as the bandwidth gets larger and larger and larger, the arctangent function becomes pi over 2. Okay? The arctangent function becomes pi over 2, and my signal-to-noise ratio becomes 2 pi over N naught B, which is just 1 over P sub N. So as remember, I'm talking about a white noise process that has a constant power spectral density for all frequencies. As the bandwidth gets larger and larger and larger and larger, the noise power gets larger and larger and larger, approaches infinity. 1 over infinity is 0. So in this case, at the input of my optimum filter, as I look at a larger and larger and larger spectral region, my signal-to-noise ratio at the input goes to 0. The message power remains finite. The noise power gets larger and larger and larger as I increase my observation bandwidth B. My signal-to-noise ratio approaches 0. All right. So let's design the optimum filter and then look at the power at the output after filtering. The optimum filter is H optimum, and this is going to be 2 alpha over alpha squared plus omega squared over 2 alpha over alpha squared plus omega squared plus N naught over 2, and you can simplify this to find it to be 4 alpha over 4 alpha plus N naught times alpha squared plus omega squared. All right. In the interest of simplifying and not writing so many symbols down, I'm going to let a new parameter, beta squared, be 4 alpha over N naught plus alpha squared, and that's just a constant. And so my optimum filter is going to be written as 4 alpha over N naught beta squared plus omega squared. Okay? That's that for this particular example. And you may be interested in the impulse response. The impulse response for this particular filter, this is the inverse Fourier transform of the optimum filter transfer function. And using Fourier transform tables that I've provided previously, this becomes 2 alpha over n naught beta e to the minus beta times the absolute value of t. All right. This is a double-sided type of impulse response. It'll look something like that. Okay, and in case you're interested, the Fourier transform pair that I used was this: e to the minus a times the absolute value of t is related through Fourier transform to this function, 2a over a squared plus omega squared. Okay, that's that. So let's calculate the power at the noise power at the output of my optimum filter. Noise power at the output of my optimum filter, P naught min, equals 2 times 1 over 2 pi, integral from 0 to b of S n of omega h optimum of omega d omega. And of course, my noise power spectral density is n naught over 2. All right, so this becomes 1 over pi, integral from 0 to b, 2 alpha over beta squared plus omega squared d omega, and this becomes 2 alpha over pi, 1 over beta, arctangent of omega over beta, evaluate from 0 to b. And this is 2 alpha over pi, 1 over beta, arctangent of b over beta. Okay? And so you'll notice here what happens is that as my bandwidth b of interest approaches infinity, my arctangent function becomes pi over 2, and my output power approaches alpha over beta, which remains finite. At the input to my optimum filter, as the bandwidth of interest became larger and larger and larger, my noise power got larger and larger and larger and approached infinity. At the output of my optimum filter, my noise power, as the bandwidth approaches infinity, remains finite. That's one payoff for using an optimum filter. All right. Well, what happens to the ratio of output signal to noise ratio to the input signal to noise ratio? Did I improve anything? Let's take a look at that. What about output signal to noise ratio to input signal to noise ratio? Did we improve anything? Well, remember what we did. We applied a message to an optimum filter and got the message back plus a distortion noise term plus filtered channel noise. So in effect, through optimum filtering, the way we're modeling this, the message stays the same at the input and the output. Therefore, the message power stays the same. The signal power stays the same at the input and output. Meaning that my signal to noise ratio out over in equals the noise at the input divided by the noise at the output. All right, and this is all because the message or signal power stays the same since we modeled distortion as an additive since we modeled signal distortion as an additive noise term, in effect at the input and the output the message remains the same, therefore the signal power or the message power remains the same. Okay? So this is really the incoming noise power divided by the output noise power. All right, and you'll recall when we looked at the input signal to noise ratio, as the bandwidth of interest got bigger and bigger and bigger, my signal to noise ratio went to 0. All right, well, proceeding. The noise power at the input is just N naught B over 2 pi. Remember, I'm working in radian frequencies now. And 1 over the output noise power is pi beta over 2 alpha arctangent of B over beta, and this is just N naught B times beta over 4 alpha arctangent of B over beta. All right. Expanding out what beta is, remember beta was 4 alpha over N naught plus alpha squared. Plugging beta back into my relationship at the bottom of this page, I get the following. I'm going to leave beta there for just a second. Turns out that if you plug in reasonable values here, this will always be greater than 1, meaning that the signal-to-noise ratio improves through optimum filtering. Okay, that signal-to-noise ratio output to signal-to-noise ratio input ratio is always greater than 1, meaning that I've improved the clarity of my message. All right. As my bandwidth of interest increases, or another way of saying it is my bandwidth approaches infinity, my arctangent function becomes a pi over 2. And so my ratio and this, you'll notice that this gets better and better and better. My signal-to-noise, my ratio of output to input signal-to-noise ratio is a function of my bandwidth. And so my signal-to-noise ratio at the output compared to the signal-to-noise ratio at the input gets better and better and better as I look at a wider and wider spectral band. So what we see here is that optimum filtering Okay? Optimum filtering indeed improves clarity while minimizing the loss of fidelity. All right, so the equations that we've seen in this example in and of themselves are not particularly interesting. What really is of interest is the process and the conclusions. And what we did was we looked at a relatively simple low-pass type message corrupted with simple broadband white noise, and we showed that as we look at the message and signal combination at the input to my optimum filtering, as I investigate that combination over a wider and wider and wider bandwidth, the signal-to-noise ratio goes to 0 because the message power dominates. And then we designed the optimum filter and showed that after optimum filtering, the noise power at the output of my optimum filter remains finite. It doesn't go to infinity. And furthermore, there is an improvement in the signal-to-noise ratio. Okay? Well, that's all I've got for today. As usual, if you have any questions, please do feel free to contact me at your earliest convenience, and I will happily answer all questions as quickly and fully as I am able. Have a nice day. Bye-bye.